what section are we? What question?
It's 3.3 number 5, I guess.
3.3, number 5.
The question is f is equal to sin x plus 1.
Okay. And what's the
Find
rest? Let me find it right here.
Find the increasing, minimum point, maximum point.
Increasing, decreasing, max, min.
Oh, I did that.
Concavity, inflections,
Yeah, the whole 9 yards.
the whole 9 yards. Just before the sketch, that's where you stop. So what's the derivative?
Sin cos x. Cos x minus sin. So you said that it goes there.
Second derivative is what?
Negative sin x minus cos x.
Okay, did it ask for intercepts?
I think it did. Didn't? No?
Oh, there is a domain.
Well, domain is everything. So
You don't have to find the domain.
Has to be between 0 and
Yeah, they give you
oh, they restrict the domain.
yeah, 0 and 2 pi.
Okay, well that makes things a little bit easier.
Yeah.
Okay, all right. So now what do we want to do? Increasing, decreasing, max, min. So this means first derivative equals 0 or undefined. It's never undefined, it's trig function, so you ignore that. Set this guy equals 0. Cosine x equals sine x. Right?
Yeah.
So this means x is equal to what? Pi over 4 or 5? Because we only want the one between 0 and 10. So they'll be equal in the first quadrant and the third quadrant because they're both negative.
Yep.
And you test those in the first derivative. Power of 4 by power of 4. And remember, we want to be stuck between 0 and 2 pi. Don't ignore everything beyond that. So plug in the number here. What number would be here?
Pi over 6.
Pi over 6 would be over here. Sure, that's a nice number. Pi would be a nice number here. Huh? 11 pi over 2.
You can just put 3 pi over 4, right?
Oh, 11 pi over 6, sure. Alright, so, and we're plugging into the first derivative, which is just this. So if I plug in pi over 6, what do I get?
Pi over 6 starts in 1 over 2. 1 over 2?
Radical over 2.
This is radical 3 over
Radical 3 over 2.
minus 1 over 2. Is that positive or negative? So this is positive here, you're increasing here. If I plug in pi, cosine of pi is minus 1, sine of pi is 0.
Negative.
That's negative. If I plug in 11 pi over 6, 11 pi over 6 is in what quadrant? Huh?
Fourth.
It's in the fourth quadrant, which means the cosine would give you positive value, sine would give you negative value. So if I plug in cosine of 11 pi over 6, what would it be? It's the same as cosine pi over 6, but the sign will change based on the quadrant, right?
Is radical 3 over 2?
They'll give you radical 3 over 2, and the sign will give you
1 over 2, negative 1 over 2.
minus 1 over 2.
Minus
So you
1
add
over
these, right? So that's plus. So this point here is going to be a max. This point here will be a min because it's defined, and this gives you the intervals of increase and decrease. So we have increasing on 0 to pi over 4, union 5 pi over 4 to 2 pi, but decreasing on pi over 4 to 5 pi over 4. We have maximum occurring at pi over 4. You plug it into here, sine of pi over 4 and cosine of pi over 4 are both radical 2 over 2. So you have two radical 2's over 2's, which just gives you radical 2. And 5 pi over 4, that puts us in the third quadrant, which means they're opposites, right? So one is positive, one. They're both negative. Is there anything else? Increase and decrease max and min, do you have to do the concavity? So now we do concavity and inflection. Which means you look at the second derivative, so you say f double prime equals 0 or undefined, and again it's not undefined, so you ignore that. This would mean set this equal to 0, you just get sine x equals minus cosine x. And this would happen at what? 3 power 4 and 7 power 4. Right? Where 3 power 4 is in the second quadrant, 7 power 4 is in the fourth. Okay, so now we have to test those two values. And a number over here, like pi over 4 is a nice thing. A number between here, pi is a nice number. A number between here. What's the number between there? Huh? What's the number between 7 power 4 and 2 pi? How do you find that?
8 pi over 4 pi.
What?
Can I put 8 pi over
8 power 4 gives us 2 pi, so that's going too far.
7 power 3.
Come again?
14 pi over
What did you say?
That's 7 power 3.
Okay, how do you know that's up here?
Because 1/4 is less than 1/3.
Okay, but what about 7 power 3? How does it relate to 2
That's
pi?
more than 2 pi.
It's more than 2 pi, because 6 power 3 will give us 2 pi, so that's going to 2
5
pi.
or 6.
Can't you just use 0 and 2 pi?
You can't? What?
Can't you use 0 and 2 pi?
I really want to test the inside.
Oh.
Although it would give you the same things, almost. But
7
You
pi
test
plus
it.
4 over 4.
11 5 or 6.
You can put
75 over 6
75 over
works.
9.
Yeah.
75 over 9.
Yeah, so your calculation's fine, I don't know.
So now you plug in power 4 into the second derivative, and what do you get? You get a negative number, right? I can think of this as just minus sine. No, it's not. Minus sine plus cosine, right? So I know that at pi over 4, both of these are positive, so overall the answer is negative. And this means concave down. If I plug in pi into here, this is 0, cosine pi is minus 1, times a negative 1. This is positive, so it's concave up. Sine of 11 pi over 6 is minus a half. And then cosine of 11 pi over 6 will be plus radical 3 over 2. This is positive, but then you multiply by a minus sign, so that becomes negative. So this guy here is an inflection, this guy here is an inflection. So we can know where we're concave up, concave down, inflection points. See where this is. Concave up. 3 pi over 4, 7 pi over 4. And we need concave down, it would be 0 to 3 pi over 4, union 7 pi over 4 to 2 pi. Inflections would happen when your x is 3 pi over 4, and 7 pi over 4. So we want the y value, so we go back to the original function. If I plug in 3 pi over 4, the sine is positive and the cosine is negative, right? But they give you the same value. So this is 0. 7 pi over 4 is in quadrant 4, the cosine is positive and the sine is negative. So that's also 0.
find that.
We're not ready for the quiz yet.
Of course you're ready. You just went through like a whole problem.
Yeah, because we couldn't do this on our own, so how are we supposed to do the quiz on our own?
You guys are telling me what to write down.
Not us guys. It was like one person. Alright.
So, I mean, sketching the graph would be like one more step where you sort of apply everything here. Are there any other questions? Yeah.
What's on quiz?
Graphing stuff.
Graphic?
Yes.
A lot of graphics.
Say we got a quiz. It's not
How many graphs I can give you? Look how long the thing is.
Do you know one of those?
Let's just get the quiz over with, but we're going to have to take it nowadays.
We just take it on Tuesday. It's so much
Say
better.
we're gonna-
I'm ready.
There's no difference, exactly.
There is a big difference. Why would you say that? It was like about.
See, someone is on my side.
Only difference is
Finally,
actually one already.
all you need is one.
The only difference is time and I need my iPad on the side of the wall.
All you need is one.
All you need is one. Okay, it's like, we'll make it like 10 minutes long. There's like 5 graphing problems, so.
You still want to take it today?
Wait, do we hand homework?
Yeah.
Do you like have to give me a heart attack every day?
What? Yeah. The web assignment. Like,
Give me some again.
what? No, you don't have to separate it.
Wow, I fell for it.
We're running the class now. There's no time to go.
You get a quiz. Everyone gets a quiz.
Why do you do this every time? Everyone falls for it every time.
Yeah, you guys fall for it every time.
I'm so gullible.
Yeah, but go for it. You can't be joking about things like
The way you like to
Who else needs one?
don't worry about that.
Who needs one?
Okay, we're going to move on to optimization. Okay, so optimization is super important topic. Most of the real world applications of calculus 1 and lands on their optimization problem. So this is really important stuff. Okay, so the whole point is to optimize something. And as you see me say here, optimize means make it as good as it can be. What does that mean? Well, often it means making something as large as possible or as small as possible. So meaning you can want to find maximums and minimums. So if you can actually rephrase a problem in this way, you can actually use calculus to figure it out. So remember, functions help us to model certain relationships in real life. So if I have a function that would model something like profits that my company makes by selling products, obviously I want to maximize a function like that. Figure out how do I get the maximum profit. If I find a function that talks about the cost my company incurs while producing the goods, then I want to minimize that function in general. That's sort of the idea. So a lot of times you can make something better by either making it as large as possible or as small as possible, and that's where optimization comes in. Right? And I gave you this whole spiel right here where you can see some more examples, but that's the basic idea. Another idea that is very important here is the idea of constraints, right? So sometimes it's not that, you want to make things as big as possible, as small as possible. Sometimes you have certain restrictions, right? You don't have unlimited resources. You have like restrictions that you have to try to make the best of. And so that is another dimension to the problem. However, once you can rephrase a problem of optimization in terms of maximizing or minimizing something, you can actually use calculus to find the best possible situation. So that's basically what we're going to do. And like related rates, there's a sequence of steps. Pretty much every optimization problem you solve using these steps. So that's nice. So let's go through the steps and then we'll go through the examples which are on the reverse side of the page. Okay, step 1, read the problem carefully. Make sure you understand what's going on. Make sure you're intimately acquainted with the problem. You know its hopes, its dreams, its aspirations. Read the problem, understand the problem, be the problem, okay? Step 2. Okay, step 2. Draw a diagram if possible. Just like in related rates, sometimes the diagram helps you figure out how to set up your equation. So that's always a useful thing if necessary. Now 3 is the important part. It's one of the most important parts and probably the most challenging part of the process is to set up equations. The difference between this and related rates is you always have 2 equations to set up, not just one, right? So I call them here the constraint and objective equations, right? So the objective equations is basically the equation that describes what you want to optimize, right? What do you want to make as big as possible? What do you want to make as small as possible? An equation that describes that quantity is your objective equation. Constraint equation is an equation that describes your restriction, right? What are you bound by? That equation is your constraint equation. Okay. We're going to go through an example. You're going to see all this, but I'm just going through what these things are. Step 4, you always use your constraint equation, solve for one of the variables, and plug it into the objective equation, right? The goal of this is to get your objective equation into a single variable, because usually we'll have several variables, and we're not in calculus 3, so we don't know how to deal with functions like that. So the next one is to, now that you have it in one variable, you want to maximize or minimize that, which we know how to do. Use the first variable, find critical points, blah, blah, blah. And then 6 is to answer the problem. So you are going to be asked something very specific, make sure you answer it, right? So if they ask you for the dimensions of a certain shape, make sure you tell them that as opposed to something else. And I'll talk more about that as well, right? Below here, I also have a note of how, when I give you these handouts, right, I gave you a couple or so already. Notice that when I have the steps, I have some words in bold and some words not in bold. Right? Yeah. So the reason for that is, the first few times you're doing the problem, you read all the steps in detail and you try to figure out and you work around it. But once you sort of start getting the hang of it, the words in bold are sort of the ones I want you to remember. Right? So after you do a bunch of problems, an optimization problem to you, this is the algorithm, right? Remember form recognition, algorithm recognition, right? So once you have, you recognize something as an optimization problem, you go into pieces, right? Terminator. And okay, I have to read the problem and understand the problem, draw a diagram, find constraint equation, objective equation, solve for one variable constraint, plug into the objective, differentiate this, find all critical points, answer the problem, right? So you have this sequence of steps that you always go through. So in your brain, these are the boldest, like the memory cues that you need to remember so that you never become, you're in an exam and you're lost, what do I do next, right? You should always know what you're doing next, right? So I just want you to remember those, that's why I put them in bold. And now, the first example is a very simple one. I'm just going to use it to illustrate going through the steps. Hopefully by the time I do that, you'll sort of get the idea, and then we'll move on to more challenging problems like the kind you would see on a final learning exam. So, let's do problem 1 and go through the steps so you can see it in action. Okay. A farmer has 100 feet of fencing and he wishes to make a rectangular enclosure. He wants the enclosure to encompass the maximum possible area so that he can plant as many crops, the maximum number of crops. What should the dimensions of the enclosure be? Okay, this is the question, right? So this is a real world problem. The guy has a fence, 100 feet of fencing. He wants to make a rectangular enclosure, right? how can he do that to get the most out of his rectangular enclosure? How can he make it the best it can possibly be? One thing you should notice here is that there are tons of ways you can make a rectangular enclosure with 100 feet, right? You can put 1 foot here, 1 foot here, right? And then here you would have 49 and 49. Possible way to make it, right? You could have 5 feet here, 5 feet here, 45, 45. Another way to make a rectangular enclosure, right? You could do anything like 10, 10, 40, 40. And there are tons of ways you can make a rectangular enclosure where the length of the fence is actually 100 feet. But the point is not to just make a rectangular enclosure. You want to make the best possible rectangular enclosure, right? The one that can hold the most crops, right? You'll notice here that they all have perimeter 100, but what do you notice about the area for this one? This one is 49. What's the area for this one? 5 times 45, 225, right? So you'll notice that from the farmer's point of view, this one is better than that one. You'll be able to hold more crops in this one, right? The area for this one would just be 40 times 10. Ah, that one is even better, right? But is that the best one, right? That's the thing. How do you find the best one? How do you find the one with maximum area that has the constraint of the perimeter being 100, right? You see, this is how the problems work. So they tell you something that they want. You want to make this as big as possible, but what are your constraints? And you have to figure out, there are tons of situations that could happen. You want to find the best one, right? So that's just trying to get you to understand the problem. Okay? So you know there are many different ways you can do this. What is the best way? So we're going to go through the steps. You read the problem, you understand the problem. All right? Draw a diagram. So step 1, done. Step 2, diagram. What can vary in all our situations? The length of the sides, right? So let me call this x, let me call that y. I want to find the x and y that makes this the best possible enclosure for the farmers, right? That's step 2, my diagram, and I label it. Step 3, so step 1, red. Step 2, diagram. What's step 3? You have to come with 2 equations, right? I want to find now my objective equation, my constraint equation. What's the objective?
What are you looking to optimize?
The thing you want to optimize. What do we want to optimize here?
Area.
Area. So the area equation would give you the objective equation. This is just a equals xy. That's an equation that describes the thing I want to make as large as possible. But what is my constraint? What am I bounded by? Yeah.
2x plus 2y equals 100.
2x plus 2y must be 100. This is a restriction. He doesn't have as much fence as he can use. He has 100 feet of fencing. He has to get the problem solved with 100 feet of fencing. Well, that just describes the perimeter, right? So you add x plus x, y plus y. The distance around should be 100. So this equation describes what my restrictions are. My x and y must fit this equation. This is what I want to make as big as possible, right? Notice that I can rewrite this equation if I wanted to. This is just x plus y equals 50. But this is the objective and constraint. Objective, what do you want to make maximize, or what do you want to optimize? Constraint, what's the thing that's holding you back? Okay. Now, what is step 4? You're always going to solve for one variable here, plug it into here, right? The problem is, you want to maximize this function, but it has x's and y's in it, and then a. 3 variables, you can't really deal with that in Calc 1. So what you want to do is get things into one variable. This is a 2-variable function. You want to get it to one variable. So how we do that? Well, x plus y equals 50. This means that x equals 50 minus y. This means that I can rewrite my area equation as the x, I simply replace with 50 minus y. So So now my x is 50y minus y squared. Now this is my area equation in terms of a single variable. Right? Now what do I want to do with the area? This is step 5. Want to maximize area. So what am I going to do? Find critical points. So I'm going to find the derivative. And find out the critical points. This means a prime equals 0. This means 50 minus 2y equals 0. This means y equals 25. Right? Now, you can test this. Right? What are the endpoints of your interval? What? 0, 100, right?
Yeah.
Now, obviously, you will notice here that you want to find the absolute maximum, as I stated here, but obviously, either of these extremes just won't work, right? If I make the length 0, I have no rectangular enclosure. If I make the length 100, then it means the width would be 0, I have no rectangular enclosure. So this guy's got to be the guy that's going to give me what I want, and so I can actually test it. Plug in 1. If I plug in 1 into the derivative, I get a positive number. That means we're increasing. Plug in 26 into the derivative, I get a negative number. That means I'm decreasing. So 25 ends up being a maximum, which is actually what I want. This means for max area, y must be 25. But x is equal to what? 50 minus y. This means that x is also 25. Now step 6. How do we answer the problem? Dimensions 25 by 25. The best possible fence for this farmer to make is having 25, 25. That is the rectangular enclosure with the largest possible area. If he wants to plant them as the most crops he possibly can, this is how we should build a fence. Okay? So this is sort of going through, and again, all optimization problems, they sort of follow this step. So let's just go over it. So we read the problem, we understand the situation, right? There are tons of ways you can do this thing. We want the best way. So we understand that by reading the problem. 2, draw a diagram that describes the situation. It's a rectangular enclosure, so I draw a rectangle. Makes sense, right? 3, I need to find 2 sets of equations, right? A pair of equations. One is the objective equation. This describes what you want to maximize or minimize. We want to maximize area, so an equation that describes area is going to be my objective. Constraint is what describes my restriction. The perimeter is my restriction, therefore I need an equation that describes the perimeter. The perimeter has to be 100, so I get this guy. The problem is, to maximize something, we need to be able to find derivatives of blah, blah, blah. This has 2 variables, so to find the derivative, I need to make it into one variable because we're only in calculus 1. So what I do is I use a constraint to help me out. Solve for one variable here, plug it into here. So now I get my area as one variable. So now I can differentiate, I find the area as a function of y, and I can find dA dy. So since I want to maximize, I know I need to find critical points, so I'm going to find the derivative, set equals 0 or undefined. It's not undefined because it's polynomial. That gives me y equals 25. Now, I want the absolute maximum of this function. Turns out the endpoints don't make sense in reality, so we ignore the endpoints. But the middle one makes sense, and then when I test it, I get a maximum. Now, it turns out, a lot of times here, you could actually skip this step, right? Because I mean, if you only have one answer, that has to be the answer, right? There's no other guys. Right? There are times, though, where you might get several answers, and you have to test them, right? To know which one is actually the maximum, which one is the minimum. So we find that, and then we get the y value, we can use that to find the x value. Step 6 is to actually answer the problem. So you have to pay attention to what you were asked for. The answer would be different if you were asked for what is the maximum area, right? So you could have described the situation and the question could be, what is the maximum area that he can enclose? Then this would not be the answer, right? The question asks for dimensions, which means they want you to tell you length times width, right? So you have to make sure you give them exactly what they're asked for. It has to be a 25 foot by 25 foot enclosure. Is there any questions on this? Yes?
Why did you use 1? Could you have used different numbers?
We've done this before. I can test any number, I feel it. I use 1 because it's easy.
But would you still give y equals 25?
That's the critical point.
No.
So I know between 0 and 100 I have to test 25. So I plug in any number between 0 and 25, plug in any number between 25 and 100.
First derivative, right?
In the first derivative, yes. We're testing this into a prime. Why? That's how I find maximums. I test things in the first derivative. The first derivative tells me about increasing, decreasing, max, and min. If I'm looking for a maximum, I'm looking at the first derivative. Yes? Do this test.
So, there's only going to be one relative test?
There could be several, but you're going to want the one that gives you the biggest.
Biggest value for...
Biggest value for the area. Right? So, I don't think you'll encounter problems where you have several relative max. You might have a problem where you have a maximum and a minimum, and obviously you reject the minimum. However, in the case where you have 2 relative maximums, you're going to find out which one is the bigger one. Right? So you take each of those and you plug into A and see which gives you the bigger A. Right? So you always have the goal in mind of maximizing this guy. This is your objective. Everything you're doing is to make him as good as he can be. And this might mean maximizing or minimizing. It depends on the problem. Here, we wanted to make the one with the largest possible area, so maximizing was what we wanted to do. Other questions?
So it's either maximizing or minimizing. There's no other case. They wouldn't want anything.
Not in California. So they will give you problems where you can phrase it in terms of maximizing or minimizing. I don't know if that's for a time. Okay, let's do another example. Let's try problem 2. Problem 2 says, design an open rectangular box with square ends. The left side and the right side should be squares. Having a volume of 36 cubic inches that minimizes the amount of materials required for construction, because of course we want to save it. Okay? So of course, step 1, you read it. Okay, good. Step 2. What do I want to do? Draw a picture, right? So here this is describing a rectangular box. So I'm going to draw a box. Right? Right? Now this side should be a square. Right? And of course that side should be a square as well. Right? So which means that the length and the width of this should be the same. So I can call this, if I call this x, then this also has to be x. The length, I don't know what the length is, so I call that something else, y. Right? That's actually that's good. Okay, so that's step 2, drawing a diagram. What is step 3? Equations. I need an objective and I need a constraint. Another way to recognize the constraint, he's going to be the guy that they actually give you a value for, right? What is something that they gave you a value for in this equation? Volume. You know the volume. The volume has to be 36 cubic inches. volume can be whatever you want. It has to be 36. This is a restriction. The volume must be 36. But what is the volume of this box?
X squared y.
X squared y. So this guy here is my constraint equation. What's my objective? What do I want to maximize or minimize?
2x squared plus.
I want to minimize area, right? So, which is, I'm going to have to,
2x squared.
the surface area is just the area of all the faces, right?
Yeah.
So what's the area of the right side?
X squared squared.
X squared, this is the area of the right side.
Plus x squared for the left.
X squared is going to be for the left side.
And 3 track rectangles.
Minus plus y.
Plus xy, this is for the bottom. Did I put something at the top? What's the top?
There is no top.
There is no top. How do I know there's no top? It's an open box. There is no top. Right? Right? This is where step one came in handy, right? So that's your equation. You can actually write this as 2x squared plus xy. Huh?
But in these two sides.
Oh, it's already.
What?
2 sides squared xy.
Okay.
3xy where?
These two.
The top.
Oh, we did we have to do the front and the back.
That's a complicated.
Bottom, front,
Yeah.
back.
Too much.
Okay? So that's 2x squared plus 3xy. Let me rewrite that. So A equals 2x squared plus 3xy. And I know that x squared y is equal to 36. So this is my constraint. This is my objective. What's the next step? Solve for someone here. Who would I solve for? I'd solve for the y because I don't want plus or minus radicals, right? So y is equal to 36 over x squared. This means I'm going to plug that for y in my expression over here. A would now become 2x squared plus 3x times 36 over x squared. And x would cancel into x, so this is just over x. Or I can write x to the minus 1 if I want. And 3 times 36 is what? 108. Okay? This is my new objective function. And what do I want to do with this function? I want to minimize the area. Because we want to save the earth. Or the whales or the pandas. Now we want to minimize A. This means that I need to find the derivative, which is going to be 4x minus 108x to the minus 2. Find critical points. What will the critical points be? X equals 0, or you would need 4x minus 108 over x squared to equal to 0, right? Obviously this rejects right away. Why would I reject that? Because sure, the derivative is undefined, but the box with 0 length, there wouldn't be no box, right? So that just doesn't even make sense to look at. So I'm going to try this one. How do I get that one to work? Solve for x. How do I solve for x? Well, I could multiply through by x squared.
4x cubed minus 1 is.
So then x cubed would be 108 over 4. Does that go into that nicely? That's actually 27? Oh, that's nice. The problems in your homework aren't that nice. Okay, so x is equal to the cube root of 27. This was a 2 of 1 power would be like the cube root of 69 over 19. Yeah, you think I'm kidding. Okay, so that would actually be 3, right? So x has to be 3. Now I know that's going to be the answer because it's the only candidate, but if you're ever very sort of skittish, you could always test it, right? Plug a number below 3 like 1 or above 3 like 4, and if you plug it into the derivative, here you would get a negative, here you would get a positive, so you know this is a minimum. So we need x equals 3, which means your y should be what? 36 over x squared over 3 squared, which is 4. So, by the way, this was step 4, this is step 5. Now we're at step 6. What did they ask us for? Oh. Well, design just, well, I guess we can tell them the dimensions. So we need a 4 by 3 by 3 box. And you can put inches here if you want. I don't need it. So that's the box you would design to fulfill this criteria.
Is there inch?
It mentioned inches cubed, so. Again, I don't really care about units, but you sort of have the idea? Yeah.
Will there be a question where there's just one critical point that doesn't satisfy
No, there has to be a critical point that will do it. Otherwise, it wouldn't be a problem.
to maximize it? We can say there's no answer. Not that bad.
Right, yeah. There would be no way to maximize it.
Okay.
And that's actually possible if you think about it. What's a good example of that? Is it possible to maximize an area with a given perimeter? The answer is yes. Could you maximize a perimeter with a given area?
I think so.
Right? Or it's one of those questions. But yes, there's sometimes it's impossible to maximize something or minimize something. So it wouldn't be a question that they asked. But here it's possible. I'll come up with some nice concrete examples next time. Yeah.
Please explain what we use the formula of area.
The formula for what? For the surface area. So I have to add up the area of all the sides. Yeah.
So the box is open.
So there's no top. It's open.
And it has nothing inside also. It has nothing inside.
Yes. All right. I guess we can stop there.